Let's have a look at finding probability of type 1 and type 2 errors from a continuous distribution. So here we've got a hypothesis test. It's one-tailed. I'm going to just focus on what happens when there's a 5% significance level. So firstly, reading the question, we're told it's a normally distributed population and we know the variance of the population. So those facts mean we can use z-scores and z-test regardless of sample size. Had we not known our variance, and it automatically tells us it has to be t-tests, had we not been told it's normally distributed, we then have to check the sample size to see if central limit theorem applies. But probability of a type 1 error, well, that's the probability of rejecting H0 given that it is in fact true. So if we draw a picture of this, it's a continuous distribution, it's a normal distribution. Here's our H0, is that mu is as it is. And here's our, it's a 5% significant level, our 5% area. So when are we going to reject H0? Well, if this curve is the true curve that we're working with, we reject H0 in here when we shouldn't do. So therefore, as long as it's a continuous distribution, the probability of a type 1 error is the same as the significance level. It's what percentage of this graph are we going to reject? Where's the rejection region? It's here, it's 5%. So that's relatively easy. Type 2 errors are always more difficult. Probability of a type 2 error. Well, that's the probability of accepting H0 when in fact H0 is false. Well, we know our null hypothesis is that mu is 30, and our alternative hypothesis is that mu is greater than 30. To be able to work out our type 2 error, we need to have an idea or a value that we're going to work with. So as opposed to saying mu is greater than 30, we need to have an idea of what value that is. So in terms of an exam question, they would probably tell you, as we've done here, in fact, what mu should be. So what's happening here is we think we're carrying out a statistical test on this curve with a mean of 30, whereas in fact, the curve should look like that at 32. And what we're doing is we're going to accept that this incorrect curve is true, but we've been working on this other curve. So let's try and put this in context. So I would always write down probability of type 2 error is the probability of accepting H0 given H0 is false. So what conditions are we accepting H0 in? So we need to work out when are we going to accept H0. So if we were dealing with our Z curve, okay, so this is Z is normally distributed, mean of 0, standard deviation of 1. This Z value here, this is going to be 5%. We can find that Z value and say that Z is inverse norm of, let's find my calculator, inverse norm of, this area is 0.95, so 0.95, and we get a mean of 0, a variance of 1. So inverse norm, area of 0.95. So that's when Z is, so our Z value is 1.645. So we're going to reject, so we're going to accept H0 if we get a Z value of less than this. So what Z value are we working with? We've got our original question is that we don't know what the value is of our sample. So what does this 1.645 convert to in here? Well, the 1.645 was worked out with our critical value. So again, if we think about, this is our curve that we're actually working with. Okay, and we think this curve has a mean of 30. This is our critical value, give us our 5% region. So what's this C? Well, how have we worked that C out? We take away the mean, which we believe to be true, and we know the variance is 9. So the standard deviation would be 3 over the square root of the sample, which is root 4, so 3 over 2. So therefore, our C value is going to be, just rearranging that, we get 1.64, I'll just use that number there. We've got that times 3 over 2 plus 30. So we get a C value of 32.47. So we've taken our Z curve on standard normal and we've converted it back to the one we're working with to work out our critical value. So we're going to accept H0 if it's 32.47 or less. So putting that into here, it's the probability that X bar, our sample, is less than 32.47, given that, in this case, the mean is now 32. So we're accepting H0 on this curve if we get a critical value of 32.47 or less. But if H0 is false, if we're given that that fact is true, then this must be true, that mu is 32. So what's the probability of this happening? Well, we can say, well, therefore, that's a normal CDF. And then we're putting in there a large negative value, negative infinity. 32.47 is our biggest value. Our mean is 32. Our variance, because of our sample, so again, think X bar is a sample. It's going to be normally distributed. Its mean is what we're testing in our hypothesis. We were told that the population variance was 9. So its standard deviation was 3. We had a sample size of 4. So we're going to put in here 3 over 2. And when we work that all out, we get mean was 32, and it was so 0.62299. Let's write the whole thing out. 22986 2213. So 0.06. That's a 0.623 for 3 significant figures. So actually, quite a big chance of having a type 2 error.